A graph is a visual representation of relationship between the given variables. The first thing that we can decide from the graph is whether the given graph represents a function or it is just a relation. And for that, we'll use something called as vertical line test. I'll draw a vertical line and I'll mark its point of intersection. Now I'll move this line along the domain of the given function. So there are two conditions. First condition is, for each and every point, there must exist an image. So that means if I'm going to move this line in its domain, so I must always get a point of intersection. So if there is any point in the domain where I don't get this point of intersection or where there is no graph, so then it is not a function. Now the second condition is, the image of an element must be unique. So that means if I'm going to draw a line at any point, there must only be one point of intersection. If I get more than one point of intersection, then it is not a function. Then it is just a relation. Now for this one, I know every time if I'll draw a line, there'll be a point of intersection and there'll be only one point of intersection. So that means this graph represents a function. Now the second thing that we'll decide from the graph is domain of a function. Now domain is the set of values of x that a function can take. So if I have to find domain of a function, I'll need to identify the region where the graph exists. Say for example, suppose I have this graph. Now for this function, the graph is defined between x equals to -2 and then x equals to +2. Now when x is less than -2 or when x is greater than +2, there is no graph. So that means if I have to write the domain of this function, I'll simply say the domain of this function is x belongs to from -2 to +2. So the third thing that I can find out from the given graph is its range. So basically range is the set of values of y. So if I have to find the range of function, I'll need to know what are the values of y that this function can take. So I'll start with this question itself. So this function, it takes all the values of y between 0 and 1. So that means the range of this function is y belongs to included 0 to included 1. Now the fourth thing that we can decide from the given graph is whether the given function is a 1-1 function or a many-1 function. Now for this, we'll use something called as horizontal line test. So I'll take up an example. Say for example, in order to decide whether the function is 1-1 or many-1, I'll draw a horizontal line and I'll mark its point of intersections. Now I'll move this line up and down. So if every time I'm getting only one point of intersection, so that means for one value of y, I'm getting only one value of x. In that case, function will be a 1-1 function. If I'm getting more than 1 points of intersection, then the function will be many-1 function. Now in this case, when I draw a horizontal line, I'm getting 2 points of intersection. So that means this function is a many-1 function. Whether the graph is an into function or an onto function, and onto functions are also called as surjective functions. Now this one is pretty simple. You'll be given a function which is defined from a to b. Now find the range of this function. So we have already studied how to find range from the graph. Now compare this range with the codomain. If the range is equal to codomain, then the function is an onto function. If range is unequal to codomain, or if range is a subset of codomain, then basically it is an into function. If range is a superset of codomain, then it is not a function. Now say for example, so I need to say whether this function is into function or an onto function. So basically this graph, it takes up all the values from -infinity to +infinity. So range of this function is y belongs to r, all real numbers. Now I look at its codomain. Its codomain is also r. Now in this case, range and codomain, they are equal. So when range and codomain, they are equal, this function is an onto function. Now the sixth thing that we'll decide from the graph is whether the function is a bijective function. Or in other words, we'll say whether the function is invertible. So if a function is both injective as well as surjective, then we'll say a function is bijective. And when a function is bijective, only then its inverse exists. Suppose a function is defined f from r to r, and I need to know whether inverse of this function exists or it doesn't exist. So first I'll check whether this is one function or many-one function. So I'll draw a horizontal line. So when I'll draw a horizontal line, I see 3 points of intersection. So basically it's a many-one function. Now when it's a many-one function, it cannot be a bijective function. Now what about this one? So when I draw a horizontal line, I get only 1 point of intersection. So that means this function is a one-one function. Now what about range? So range is from 0 to infinite and codomain is also from 0 to infinite. So when range and codomain, they are equal, this function is an onto function. So now when a function is both one and onto, it's a bijective function. Now the seventh thing that we can do is, if we know a function is invertible, we can draw the graph of its inverse function. So suppose I have a function which is defined from a to b, y equals fx, and suppose this function is a bijective function, then its inverse function f inverse will be defined from b to a. So its inverse function will be defined from b to a, and it will be defined as y equals f inverse of x. Now how do we draw the graph of inverse function? Now there are two methods. The method one is by taking the reflection about y equals to x line. Say for example, a function is defined from r to r, and this function is defined as y equals x cube. So I'll draw the graph of y equals to x cube. So first I'll draw horizontal lines. So I'm getting only 1 point of intersection. So this function is a one function. And what is the range of this function? So it takes all the values from minus infinite to plus infinite. So its range is y belongs to r. Now range and codomain, they are equal. So this function is both 1 and on. Now that means inverse of this function exists. Now inverse of this function will be defined from r to r. So f inverse will be defined from again r to r. And in order to write its inverse function, what I'll do is I'll interchange x and y. So I'll write x equals y cube, or I can simply write y is x to the power 1 by 3. So inverse of the function y is equal to x cube is y equals x to the power 1 by 3. Now we'll draw the graph of cube root of x. So one way of doing it can be, so on the graph of y is equal to x cube, I'll draw this y is equal to x line. And then take the reflection of the graph of fx about y equals to x line. So if I take the reflection of this graph, so I can draw this graph as, so this is the graph of y equals x to the power 1 by 3. Now we'll come to the eighth thing. Now eighth thing that we will decide from the graph is whether the function is a periodic function or it is a non-periodic function. If my graph has some pattern which repeats after a certain interval every time, then I'll say my function is a periodic function. Now say for example graph of y equals to sine x. Now when I look at the graph of sine x, I see this pattern. Now this pattern, it gets repeated every time. So it is a periodic function, and the length of this interval is called as fundamental period of that function. So in the case of sine x, the fundamental period is 2 pi. Now the ninth thing that we'll decide in a graph is whether the function is a continuous function or a discontinuous function. So if the graph of function is connected, then we'll say the function is continuous. And if the graph of function is disconnected at any point, then we'll say this function is discontinuous at that point. So in order to decide whether the function is continuous or discontinuous, all you need to do is you need to draw the graph, and if while drawing the graph my pen lifts, then the function is discontinuous at that point. And if I don't need to lift my pen, then the function is continuous. Say for example, now this function f is defined from r to r. Now I need to know whether this function is a continuous function or a discontinuous function. So if I'll try to draw this graph again, I don't need to lift my pen, right? So that means I'll say this function is continuous for all real numbers. So this is continuous in all x belongs to R. Now the 10th thing that we'll decide in a graph is its differentiability. whether a function is differentiable or not differentiable. Now for differentiability, there are two steps. Now step number 1, discontinuity implies non-differentiability. If function is discontinuous at some point, I'll straight away say this function is also not differentiable at that point. Now second thing is, what if a function is continuous at a point? If function is continuous at a point, I'll need to check its differentiability. If at any point the function changes smoothly, then the function is differentiable at that point. Now if a function has sharp corners or a cusp or a point where it has a vertical tangent, then so at that point the function will be continuous but it won't be differentiable. Say for example, so suppose this is the graph which is given to me. Now when I look at this graph, I know if I'll draw this graph, my pen is going to lift at 0. So it is discontinuous at x equal to 0. So this function is discontinuous at x equal to 0, but at all of the points this function is continuous. So there is only one point where this function is discontinuous. Now when we talk about differentiability, clearly I know because at 0 this function is discontinuous, it is not differentiable at x equal to 0. Now I see an edge at -2 and +2. So because I see two different tangents at -2 and +2, this function will also not be differentiable at x equals to -2 and x equals to +2. So this function is discontinuous at x equals to 0, and this function is not differentiable at x equals to 0, x equals to +2 and x equals to -2. Now the 11th thing that we can decide from the given graph is its interval of monotonicity. I can find the interval where this function is increasing, and I can also find the interval where this function is decreasing. So if the value of function increases, I'll say it is an increasing interval, and if the value of the function decreases, I'll say it's a decreasing interval. Now this function is first increasing from -infinite to 0, and then it decreases from 0 to infinite. So that means from -infinite to 0, this function is an increasing. From 0 to infinite, this function is a decreasing function. Now the 12th thing that we can decide from a graph is its critical points, and also from these critical points we can say whether it is a point of minima or a point of maxima. Now there are two kinds of critical points. So first, all the points where the function is not differentiable, and secondly, points where I have a horizontal tangent, that is the points where derivative is 0. Say for example, so this function is not differentiable at x equals to -2, x equals to 0 and x equals to 1. So these are my first set of critical points. Now I'll also need to find the points where I may have a horizontal tangent. So if I look at this point, maybe I'll say this point is -1. So at this point, if I'll draw a tangent, this tangent will be horizontal. So I'll get another critical point, and there will be x equals to -1. So this function, it has 4 critical points: -2, 0, 1 and -1. Now the 13th thing that we'll study in a graph is its concativity, and to know whether any function has a point of inflection. So there are two kinds of graph. The graph which are concave up and the graph which are concave down. So basically we can determine concativity by second derivative, d2y upon dx square. If second derivative is positive, it is concave up, and if second derivative is negative, then it is concave down. At point of inflection, the concativity of graph changes. I'll draw a graph. Now before x equals to 0, this graph is concave up, and after x equals to 0, this graph is concave down. So that means this point x equals to 0 is point of inflection. Now I take another one. Now in this case, when x is less than 0, the graph is concave down, and when x is greater than 0, graph is concave up. So that means again the concativity changes at 0. So at x equal to 0, this again is point of inflection. Now at 0, when I look at the value at 0, so value at 0 is 0. Now the graph right before 0 is above this line, and the graph right after 0 is above this line again. So 0 is also a point of local minima. So it's a point of local minima and it is a point of inflection. For some functions, we can find the value of definite integral using graphs. So it may not necessarily be true for each and every function, but then for certain functions, we can definitely calculate the value of definite integral. Say for example, this box x represents greatest integer function. So we'll actually draw this graph when we'll study its transformation, but right now I'll just draw the graph. So at this point, don't bother about from where this graph has come. So the graph which I have drawn in green is actually the graph of this function of y equals 2 upon e to the power x. Now, if you have studied definite integral, then definite integral is the area of the graph with x-axis with plus or minus sign. If the graph lies above x-axis, we'll take a plus sign, and if the graph lies below x-axis, we'll take a minus sign. So now in this case, the only area which is possible is this rectangle which is between 0 and log 2. So the value of this definite integral is log 2. Now the 15th reason why we should study graphs is area under the curves. Now area under the curves is one such topic which will require the extensive use of graph. So whether if I have to find area bounded by the curve and x-axis, or area bounded by the curve and y-axis, or area bounded by multiple curves and x-axis, or area bounded by two given curves, I'll need to draw the graph before I can start solving the problem. Now the 16th application of graphs is perhaps one of the most interesting and fascinating applications of graph. So we can use graph to find number of solutions of an equation. Now suppose I have this question where it says fx equals gx, and I need to find number of solution to this equation. I can draw the graph of y equals to fx, and then I'll also draw the graph of y equals to gx. Now I need to find all those points where the value of fx is equal to value of gx. So what I'll do is mark all the points of intersection. So therefore the number of solutions to this equation is equal to number of points of intersection of these two graphs. So in this case, the number of solution of this equation will be 4. So if we have to find number of solutions of any equation, then we can simply draw the two graphs and we can find their points of intersections. Say for example, cos x equals x square. So if I'll draw the graph of cos x, I will go on, and if I'll draw the graph of x square, so now these two graphs, they have 2 points of intersection. So number of solutions of this graph will be 2. Now the 17th application of graph is solution of inequalities. So suppose I have any inequality which says fx is greater than gx. Now one way of doing it can be, I can draw the graph of fx, I can draw the graph of gx. Now in order to solve this inequality, first thing that I'll do is I'll find their point of intersections. So I'll solve this equation fx equals to gx and I'll find their point of intersection. Suppose x equals to a, x equals to b, and this is x equals to c. Now I need to solve this inequality. So I need to find the interval where fx is greater than gx, or the interval where the graph of fx lies above the graph of gx. Now the graph of fx, it lies above the graph of gx in this interval and in this interval. Now also It doesn't have an equality sign, so I'll use open circles. So answer to this inequality will be x belongs to, so from minus infinite to a union b to c. Now say for example, sin x is less than or equal to cos x between 0 to pi. So between 0 to pi, this is the graph of sin x, and I'll draw the graph of cos x also. So that is the graph of cos x, and the point of intersection is pi by 4. So blue graph, it's a graph of cos x, and this red graph, this is a graph of y equals to sin x. Now I need to find the interval where the graph of sin x lies below the graph of cos x. So the graph of sin x lies below the graph of cos x in this interval, and because it has an equality sign, so I'll include it. So in this interval from 0 to pi by 4, graph of sin x is actually less than graph of cos x, but from pi by 4 to pi, the graph of sin x is greater than graph of cos x. So answer to this inequality will be x belongs to from 0 to pi by 4, 0 included and pi by 4 also included. Now these 17 cases clearly illustrate how imperative it is for us to study graphs.